Hello. In this paper, we will introduce our recent research on how to solve the solution path for sparse regression model with automatic feature grouping. This is joint work with my student Binggu and Guodong Liu, because both of them have visa issue. So I will do the presentation. So this work has been done by my group when we at UT Arlington. My group moved to University of Pittsburgh now. So in this presentation, first I will give the background introduction on the feature selection and also review the Oscar model. This is a basic model we target. And then we propose our new group keeping solution path algorithm. And also I will introduce our epsilon approximation analysis. Basically, it's an error bound for our algorithm. And then I will show our experiments to evaluate the advantage of our new algorithm. Then I will conclude the presentation. Now in data mining applications, especially in the big data area, many data have very high dimensional data. For example, in genetic data, usually we need address more than 500,000 genetic bases. And in pathological images, each image we have more than 20 gigabytes of data, so the dimension is extremely high. To address this such high dimensional data problem, the feature selection method is very important. Basically, we want to identify the significant features associated to the response variables. So such variables can enhance the prediction tasks and also give us inside information, especially in bioinformatics, computational medicine research. The selected features could be the biomarker to help the drug design and therapy. In recent years, the major feature selection method mainly focus on the sparse linear models because they can give us very good result. At first, the lasso method was proposed, and also multiple different versions of lasso model was proposed. So they impose the L1 norm as regularization. Later, the group lasso method usually use the L1, L2 norm, the mixed norm. In this way, we can group variable together to select variable in grouped manner. However, for lasso problem, basically we want to select only one or several important weights from different highly correlated features. In biomedical research, many features usually work together. For example, if you decide the vessel growing, so actually 4 genes come from the same family, they always work together to decide the result. That means multiple features, they highly correlate to each other to lead the results. So when we do the feature selection, we cannot only select one from them. We should select both a group of features. So then the regular L1 norm-based sparse model cannot select such a group-wide feature. Basically, they only select one from them. The other types of method, like the group lasso method, they require the feature group information before we do the feature selection. However, in the practical case, that's impossible because we don't know which feature, which group we have. So we want to discount them from the data. So then these two disadvantages really limited the current sparsity model to do the feature selection. So it's crucial to design a new feature selection method with automatically identifying homogeneous groups of features. So to address this problem, in the literature, many groups already noticed that. So multiple methods were proposed. For example, elastic net, fuse lasso, class lasso method. For this method, basically make a constraint between some relation of the weights of features. However, they didn't consider the pairwise relations. As a result, so this method cannot really identify the feature group structure. So in 2008, there is one method called the Oscar method. This method is actually they can address this problem pretty good. So they encourage the equality of coefficient of the highly correlated feature by the pairwise L infinity norm. So the basic idea is to adaptively capture the feature groups by enforce pairwise infinity norm to every pair of the features. So after they learn the model, then they can automatically learn the feature groups. So that's why in this paper we focus on the obstacle model because they can automatically do the feature grouping. In sparse linear model, we know that tuning parameter is tedious work. First, this model using penalty terms to add sparsity. Then we have to tune the parameters. On the other hand, the sparse linear model at least they are non-smoothing, sometimes even non-convex. So the optimization very slow. So when we do the parameter tuning, it's very tedious. So to address this problem, Hesti, Friedman et al. They propose to calculate the solution path. So the solution path basically, for example, here I show on figure. This is a solution path for lasso problem. For lasso problem, the lambda, the parameter of the penalty term, can be selected by different values to then leading to different results. Solution path basically can tell us all the possible parameter values corresponding to the result. So then we can easily select the parameter that we can do the model selection. So that will be very fast. So in literature, multiple solution path algorithm were proposed for lasso problem, L1 norm SVM, L1 norm generalized linear model, and also generalized lasso. However, so far there are no solution path algorithm for Oscar model because the penalty term is very complex. It's complex because we use a pairwise L infinity norm. There are lots of L infinity norm, so it's very difficult to calculate the solution path algorithm. That's a contribution for our paper. We provide a way to calculate the solution path for Oscar model. Well, and also we noticed that there is a accelerated proximal gradient algorithm were proposed by James Cox group. So they proposed called a fast Oscar solution. So this algorithm can faster calculate optimize Oscar model. However, when they tune the parameter, they also use gradient search. That means they cannot calculate the solution path. However, their model can help us get a good initialization. So our motivation is to calculate the solution path for the pairwise L infinity norm. So given a set of homogeneous group of features, for example, we can use a batch algorithm like a fast Oscar to calculate the model first because the model is convex. So when they get the model, that means for one parameter lambda, one set of parameter lambda 1, lambda 2, they will give a result. Based on this result, and also given error bound epsilon, that means our solution will be approximate solution within under the error bound epsilon. So we can find all the solutions and for all the different lambda parameters of lambda 1, lambda 2, such that user can easily find the optimal parameters. So the Oscar model, they train this I showed on the left panel of the slides. So we normalize both data and the labels. So when we do classification, then we need using positive one and negative one as a different group of labels, then normalize them. And the feature, we also do the normalization. So the Oscar model, they have the first, they have loss function, plus the first regularization is a standard lasso regularization. The second regularization is the pairwise L infinity norm. That means we find all the pair between the feature weights, then impose the L infinity norm. If lambda 1 equal to 0, oh, there's a typo here. If lambda 1 equal to 0, that's a standard lasso problem. If lambda 2 equal to infinity, that means we cluster all the features as one group. So on the right panel shows the search the solution area of the Oscar model. So when lambda 1, lambda 2 get different values, the optimal solution will be different. So how can we find a solution path for all of them? It's non-trivial. So tuning parameter is very time consuming. So to calculate solution path, first step we need to calculate the optimality conditions for obstacle model. Since we have all the ways, first we can use the fast obstacle, the existing algorithm to calculate one solution. Based on this solution, we can sort all solutions. That means we sort all the beta. That's the weight of all the features. And then all the features, they have the group. We also sort the group information. For each group, they have one set value. That then we can get set 1, set 2, till to set G. That's every group they have one value. So within group, the feature have the same weight. Different groups they have different weight. Based on this notation, we can rewrite the original obstacle model. So here the theta will be the sorted weights, and the WG will cover both lambda 1 and lambda 2 based on the trade-off. So based on new objective, we can using the KET condition get the automatic condition for obstacle model. So and we introduce two sets. One is the active set, one is the inactive set. So when the group value is non-zero, we call active set. When they turn to 0, then we call inactive set. So the equation 2, 3, and 4 to show the optimal condition for obstacle model. So when we find the solution path, basically we want to find every step what's the adjustment for lambda and also the direction for the solution. So for the parameter we have lambda 1, lambda 2, so we have 2 adjustments. Then we introduce a D to balance them. D is the balance, the ratio between 2 values. For example, we let D1 is 1. So D2 can be like 0.5, 1, 2. Basically, we use these several values in our experiments. Then we have 3 key steps. The first step to calculate the direction of the lambda theta. That means the gradient, the direction. The second step will calculate the maximum adjustment. So how much we can go further. The third step we need to calculate the duality gap. So because we consider when we calculate solution, we find all the possible approximate solution below the error bound, below the accuracy bound. So we use the duality gap to bound that because the duality value of the approximation is the upper bound between the current solution to the optimal solution. So the duality gap can be the bound for the errors. So we have 3 conditions. So when the parameter have an adjustment, the first condition is some group becomes 0. Then that will be the first case. Sometimes some groups the change order will be the second case. The third case, well, the duality is larger than epsilon, larger than error bound. That means we have to stop. We cannot find. We don't have good solution. If we don't have good solution based on the current parameter, we need to recalculate the optimization result, then redo the solution path. That's why we have multiple intervals. Similarly, in lasso solution path, we can see there are lots of intervals. So the algorithm basically first with a fast obstacle to calculate the initialization based on a pairwise lambda 1 and lambda 2. Then we repeat calculate the direction for lambda theta and the delta theta and the delta enter. Then update the enter theta and the lambda 1, lambda 2. Repeated until the duality gap is beyond the errors. So the key step is how to calculate lambda theta direction and the delta theta direction and the delta eta and the duality gap. So I'm going to show that. First one to calculate the direction of the delta theta. So because for the theta value equal to 0, then we don't need to consider that. So only need to consider the theta, the group value. They are still in active set. In this case, then for the duality, for the first optimality condition, we can calculate the gradient. So we can find the direction. That's the equation 5. We can find the relation between the delta theta and the delta eta. Then the equation 6, we write them in the metric formulation. In the metric formulation. For metric formulation, then we define the psi. Psi is denote the direction of the data set with respect to the data enter. Then for H, we don't do inverse here because we don't need to consider the zero part. So we do the QR decomposition for H, so we can calculate cosine. After we calculate cosine, we know the direction of the data set and the data enter. Then we calculate the 3 cases for data enter. That's the largest step we can go for all 3 cases. Then we use the minimal one because we need guarantee all 3 cases should be satisfied. Then for duality gap, we have that's a standard formulation because this one was proposed by previous work. So based on this equation, we can calculate the duality gap. There will be the errors for the current step. Now for every step we go there. We don't want to beyond the errors. Our main contribution proves this theorem. First theorem, for every interval, our solution can cover all the solution, satisfy the solution will be good solution. Beyond the errors is below the error bound. And combine all the interval solution together, we will get our final good solution path for the whole problem. So we verify our result on 9 benchmark datasets. So first, we calculate the every result over 10 trials for our the solution path algorithm. We can see that when we fix D1 as 1, then D2 get the 0.5, 1, 2 different values. So within finite iterations, we can calculate all the solution paths. Because when we have an interval, we need to recalculate the fast outcome, other method. So on the right side, we show that how many times we rerun them, but it's a small number. It's only several times. We can consider if we will tune the parameter, we need to run them many times, at least several hundred. They will be very slow. That's why when we compare our method and the fast outcome method, if we tune fast outcome method, get the best result, or using our method, using solution path find the best result, our method will be much much faster, because on the y-axis shows the running time based on the second. So the red line show the result of our method. We get a much faster result. And also we compare the errors of the training and testing errors, and also we always get better, sometimes better, sometimes comparable result, equal or better result, because our solution path to guarantee find all the possible solutions for the parameters. We can select the best ones. And also, we also show the result compared to the last method and the Oscar model to show that we really can automatically identify the group information. For example, we found from the 1 benchmark dataset, we select 6 features. Each feature we duplicate 20 times. So then we add the Gaussian noise on that. So if we run the last method, we can, from the first figure, we can show that most features will be suppressed to 0. Their weight will be 0. Only several features are selected. That's wrong result, because we know most of them they should be non-zero. If we run Oscar model, we can see that we can recover the group-wise the weights for all the features, find a good 6 groups. So from this experiment, we can show that the Oscar model can really automatically identify the feature group. So in this work, we propose a novel group keeping solution, solution path algorithm for Oscar model, such that we can quickly find the result, because we consider lots of pairwise L efficient norm is very slow to solve. So if we have very large scale data, then the existing method doesn't work. However, our method can give us good solution paths. We can address the large scale competition for automatic feature grouping model. Our current work, we try to extend this model, the solution path to the general structure sparsity methods. Yeah, we are grateful to the support from both NSF and NIH. Thank you.
Any questions?